So today is just going to be a revision. We'll go over questions from all three of the modules. So this is labeled the basic tutorial, but they're a bit more advanced, these questions. So yeah, like a lot of the questions in the exam so you'll have 20 questions, and about, I'd say half of them will be like basic, and then you'll have a few intermediate and then a few hard ones. So today's questions in the basic tutorial will be like a bit harder than your basic questions, more like intermediate. And there's so don't be too worried if you think this is a bit harder. Okay. So number one, we have a bird flying horizontally at a height of 20 meters with a speed of 15 meters per second, and it drops a stone. If air friction could be neglected, at what speed would the stone hit the ground? So the stone, the initial velocity of the stone, right? So we've got the stone here. It's initially horizontal. Yep. So there's some more basic worksheets coming. Chris is printing them out. So we have the initial velocity, which is 15 meters per second horizontally, okay? And once the bird drops the stone, it's going to accelerate downwards, and eventually it will hit the ground, right? So we want to know the velocity. We want to know the speed when it hits the ground. Okay. So this speed will have a horizontal component. So it'll have a horizontal component, and it will also have a vertical component. Okay, so okay, and we want to know what this will be. So the total, we'll call this V total, is equal to question mark. Okay, and so the horizontal component of this stone isn't going to change because there's no air friction. Okay, so the horizontal component, which was originally 15 meters per second, so the horizontal component will be 15 meters per second when it hits the ground. And so now we need to find the vertical component, so Vy is equal to question mark. Okay, so the way you're going to figure out the vertical velocity is using, so we want to know the vertical speed when it hits the ground. So we know that if you drop an object from a height, it's got potential energy, and as it drops, it's going to gain kinetic energy. So there's no air friction. So the kinetic energy when it hits the ground will be equal to the potential energy that it had at the top. So Ke is equal to Pe, potential energy. And if that's the case, you can use this equation here. The velocity will be equal to the square root of 2 times gravity times the height. Okay, so I showed this equation in our first tutorial, I think. It's just a little shortcut, so it just comes from this equation here. And so the vertical velocity will be the square root of 2 times 10 times the height, which is 20. And that will give you 20 meters per second. So this vertical component will be 20. And so the V total will be the square root. So we're going to use Pythagoras. 15 squared plus 20 squared, which will give you 25 meters per second. So,
sorry, Tom, there's the rest of those 12 more, but I'm afraid you'll have to staple them yourselves or put somebody to work doing it, because I've got another meeting.
Okay, thank you. All right. All right, so our speed will be 25 meters per second. Okay. Number 2, the acceleration due to gravity on the moon is 1.62 meters per second squared. A rock is launched vertically upward from the surface of the moon with an initial velocity of 6 meters per second. What's the maximum height that the rock will reach? So we know that the acceleration will be equal to negative 1.62 meters per second, meter per second squared. So, and we're saying that acceleration will be negative because it's downwards and our initial velocity is upwards. So our VI initial velocity is 6 meters per second, and so that will be positive. And we want to find the maximum height. So when it's at the maximum height, the final velocity will be 0. So Vf is equal to 0 meters per second. And so we want to find the vertical distance, which is the height. So d is equal to question mark. Right, and then your equation will be d is equal to Vf squared minus Vi squared over 2 times A. Okay, so that's one of your kinematics equations that you should have on your cheat sheet if you haven't got it already. So Vf is 0, so 0 squared minus Vi squared, which is 6 squared over 2 times negative 1.62. And that will give you 11.1. 11.1 meters is the height that it will reach. Okay. Number 3, we have a cart, a 2 kg cart moving at 3 meters per second to the east, and it collides head on and elastically. So that's your keyword there, elastic, with a stationary box which then moves to the east at 2 meters per second. So the box is moving to the east after the collision at 2 meters per second, and we want to know the velocity of the 2 kg cart after the collision. Okay, so if we have an elastic collision, then the kinetic energy is conserved, and that means you can use this equation. So V1 minus V2, so the difference between the velocities so this is before the collision, will be equal to V2 minus V1, and this is after the collision. Okay. So here, let's say that V1 is the cart and V2 is the box. So I'm just going to write this out. So V1 is the the cart. So before the collision, V1, the cart, was moving at 3 meters per second to the east. So that will be 3. So let's say east is the positive direction. And the V2 is going to be the velocity of the box, which was stationary before the collision, so that's 0. And then after the collision, so V2 is the box. So the box is moving at 2 meters per second to the east. So that's 2. And then minus the velocity of the cart after the collision. But we don't know that, so we'll just leave it as V1, right? So then if we want to get V1 on its own, so then 3, so this side will be 3 minus 2. So 3 minus 2 is equal to negative V1. And then, so we want V1, not negative V1. So V1 will be equal to negative 1. Okay, so the 2 kg cart will be going backwards after the collision. Right, so you can see that the difference in velocity between the two objects has been maintained. So before the collision, there was a difference in velocity of 3 meters per second. So the cart was moving at 3 meters per second, and the box was stationary, so that's a difference of 3. After the collision, the box was moving at 2 meters per second to the right, and the cart is now moving at 1 meter per second to the left, so that's a difference of 3 again, right? It's just now going in the opposite direction. Okay, so you'll see that in that question you don't need to use the mass. Okay, you can use the mass if you want to, but that's going to be harder, and you want to make things as easy as you can. So number 4, we have a 4 meter long, thin, rigid, uniform plank with a mass of 16 kilograms lying horizontally on the ground. Your 24 kg brother is standing on the plank 1 meter from one end. What force will you need to exert on the other end of the plank to lift it off the ground? So we're going to draw our plank. So here's our plank. Right. So we've got our 24 kg brother, 1 meter from the end. So he's going to exert a force downwards of 240 newtons, right? And then the center of mass of the plank is going to be acting in the middle. So the center of gravity will be right in the middle, which is where the weight force, the 16 kilograms, will be acting. So in the middle of the plank, it's going to be 160 newtons. Okay. So I'll just write down the distance. So let's say the fulcrum will be here. So this is our fulcrum on the other end from where we will apply our force. So we're going to apply our force at this end here. Right? So we want to find out how much force we have to apply. Okay. So let's call this F1, and let's call this F2, and let's call this F3. Okay, and so this is 1 meter, and that's 2 meters. Okay. So it's not quite to scale, but all right. So then we're going to solve this by saying that the clockwise torque is equal to the counterclockwise torque. So that will be the minimum force that will be required. So it needs to exceed that force, because that's the force required to keep it horizontal. And then so that's going to be the minimum force in order to lift it. Okay. So if the fulcrum is here, which forces are making it go clockwise? So F1 and F2 is going to make the plank go clockwise like this, right? And F3 is going to make the plank go counterclockwise like this, right? So we have two clockwise forces and we have one counterclockwise force. Okay, so this one's a little bit harder. So you have the torque clockwise is equal to the torque counterclockwise. So the clockwise torque is made up of two components. You have F1 d1 plus F2 d2 making up, so these two making up the clockwise torque, and then the counterclockwise is made up of just force 3, so F3 d3. Okay, so F1 is 240 times 1 d1 plus F2, which is 160 times d2, which is 2, equals F3, which we don't know. So F3 times d3, so that's going to be 4 meters because you're exerting the force right at the end, and it's 4 meters from the fulcrum. Okay, so then 560 is equal to 4 times F3, and then F3 is equal to 140. So F3 is equal to 140 newtons. Okay, so that one's a little bit harder. We have 3 components here, not 2. Okay. All right. So number 5. We have a spring with Hooke's law constant of 200 newtons per meter, which has been compressed by 0.1 meters in a toy gun. When the spring is released, it accelerates a 10 gram or 0.01 kilogram bullet out of the gun. What will be the maximum speed of the bullet? So we're looking for V max. So V max is equal to question mark. So the kinetic energy of the bullet is going to be coming from the potential energy that has been stored in the spring when it's being compressed. So when you compress a spring, it doesn't want to be compressed, so it's got potential energy, right? And then that potential energy in the spring is going to be transferred into the bullet, and that bullet will gain kinetic energy. So on the cheat sheet that I uploaded, I've just got a shortcut, which is when the kinetic energy is equal to the energy that's being stored in the spring, if that is the case, then you can just use V max is equal to the square root of K, which is the spring constant, times the amplitude squared over the mass. Okay, so here we've been told the spring constant K is 200, and the amplitude, so that's the amplitude is the maximum compression. So the maximum compression is 0.1 meters, so that's our amplitude, 0.1 meters. So, and our mass is going to be 0.01. So we'll just put our numbers in now. So 200 times 0.1 squared over 0.01, and that will give you 14.14 meters per second. Okay, So this is quite common where they'll ask you for the velocity of whatever's been propelled out of the spring. Okay, so that's the reason I've put this rearrangement here. So just recognize that. It's when the kinetic energy of the whatever's being propelled by the spring is equal to the energy, the potential energy stored in the spring, then you can use this equation to find the maximum velocity. Okay. Number 6, so now we're moving on to solids and fluids. We have a small piece of ice which has a volume of 1.63 times 10 to the negative 3 meters cubed. We want to reduce the volume of this piece of ice to 1.6 times 10 to the negative 3 meters cubed. By how much must you increase the pressure of the surrounding environment to achieve this? So for this is bulk modulus. We've been given the bulk modulus of ice, which is 2.2 times 10 to the 9. So the equation for bulk modulus, so B is bulk modulus, and that's equal to the negative of delta P over, so delta P is the change in pressure, and that's over the delta V, which is the change in volume, over the original volume, VO. Okay, so that's your equation for bulk modulus. And the reason for the negative sign there is because when you increase the pressure, the volume decreases, and when you decrease the pressure, the volume's going to increase, right? So if you compress something more, the volume's going to decrease, sorry. So that's why the negative sign's there. So here we want to find the pressure change, so the increase in pressure. So we're going to rearrange this equation for delta P. So delta P is equal to the negative of the bulk modulus times delta V over VO. So the bulk modulus, so negative times the bulk modulus, which is 2.2 times 10 to the 9, multiplied by the change in volume. So the change in volume here is 0.03, so negative 0.03 because it's reduced. 0.03 times 10 to the negative 3 meters cubed. So negative 0.03 times 10 to the negative 3 cubed. And that's over the original volume, which was 1.63 times 10 to the negative 3. And that will give you 40,490,797 pascals. So we want that in megapascals, so you'll just divide that by 1 million or 10 to the 6, and that will give you 40.5 megapascals. Okay. So number 7, we have a cylindrical container holding a gas at a pressure of 1.5 atmosphere. Each end of the cylinder has an area of 40 centimeters squared. What force does the gas exert on each end of the cylinder in newtons? So we want the force, and we've got the pressure and the area. So the equation that we're going to use is pressure is equal to force over area, and of course we want the force, so we're going to rearrange it for force. force is equal to pressure multiplied by the area. Okay, so this one here is a little bit trickier because they've given you the pressure in atmospheres. So 1 atmosphere is equal to 101.3 kilopascals. So you need to have your pressure in pascals before you enter it into your equation. So our pressure here, our pressure is equal to 1.5 times 101,300 pascals. So 1.5 times 101,300, which is equal to 151,950 pascals. Okay, so it's very important to read the units carefully to make sure that you don't get caught out. Otherwise, you'll get the wrong answer. And the area is being given to you in centimeters squared, so that has to be in meters squared. So area. So centimeters squared will be 10 to the negative 4 times 10 to the negative 4. So we're going to go 40 times 10 to the negative 4 meters squared. Okay. So now we can put our numbers in. Force is equal to pressure times area, 151,950 times 40 times 10 to the negative 4. So that will be 608 newtons. Okay. All right. So number 8. A sphere has a volume of 1 meter cubed and an unknown density. When it's floating, so it's floating on the surface of a bath of water, it displaces 0.5 meter cubed of that water. What is the density of the sphere? And we've been given the density of the water. So first of all, if an object is floating, it means that the density of that object is less than the density of the liquid that it's floating in. Okay, so if the density is less, it'll float. If the density is greater, it's going to sink. Okay. And so we know that the density of the sphere has to be less than 1,000 kilograms per meters cubed. Okay, so well, that would automatically eliminate your options D and E. And then the next thing to know is that here we've got a volume of 1 meter cubed, so that's the volume of the sphere, and it's displacing 0.5 meters cubed, which means that 0.5 meters cubed is underwater. So that means that 50% of the volume, 50% of the volume is underwater. Okay, so 50% is underwater. It means that the density of the sphere is 50% of the density of the liquid. So the density of the sphere is going to be just half of the density of water, so half of 1,000. So density of sphere is equal to 50% times 1,000, the density of the water. So that's going to be 500 kilograms per meters cubed. Okay, or 5 times 10 to the power of 2. Okay. So that's always the case when it's floating. If 20% is underwater, that means that the density is 20% of the density of that object is 20% of the density of water. Okay, so that's a good rule to remember. Okay. Right, and then number 9, we have a horizontal pipe with a cross-sectional area at point A of 0.3 meters squared. The diameter of the pipe increases smoothly so that the cross-sectional area of the pipe at point B is 0.8 meters squared. If water flows in the pipe at point A with velocity of 4 meters per second, what's the velocity of the flow at point B? So here we've got the area, the cross-sectional area, and the velocities. So the equation is A1V1 is equal to A2V2. Okay, and we want to have velocity at point B, which is going to be V2. Right? So we're just going to rearrange this equation. V2 is equal to A1V1 over A2. So area 1, the area at point A is 0.3 times the velocity at point 1, which was 4. And then the area at point 2, or area at point B, is 0.8. So that will give you 1.5. So V2 is 1.5 meters per second. Okay, so next page, number 10. We have a viscous fluid, so that keyword viscous. Fluid flowing through a horizontal pipe that's 1 meter long and has a uniform radius of 1 centimeter. The pipe has a piston at one end and is open to the atmosphere at the other end. When a force of 24 newtons is applied to push the piston, the fluid flows out of the pipe with a volume flow rate of 3 times 10 to the negative 2. What's the viscosity of the fluid? So here we're looking for viscosity, which is this symbol here, right? And so because it's a viscous fluid, we're going to use our flow rate equation. So flow rate is equal to delta P times pi times r to the power of 4, so radius to the power of 4, over 8 times viscosity times the length. So here we're after the viscosity, right? So if it's on the bottom here, we want to rearrange for viscosity, so we can just do a swap here. So then it will be viscosity is equal to delta P pi times radius to the 4th power over 8 times the flow rate times L. Okay, so we've just done a straight swap. So viscosity is equal to delta P. So we haven't been given the difference in pressure here. What we've been given is the force. So I'm going to rub this out. I'm going to rub this off the board here so I have some space. So we have to figure out what delta P is going to be. So the change in pressure, remember, is the change in force, or the difference in force, over area. So we have a force of 24 newtons being applied. So that's 24. And the cross-sectional area, we can determine that from the radius. Okay, so the radius is 1 centimeter or 0.01 meters. So that's going to be the cross-sectional area is equal to pi r squared. So A is equal to pi r squared. So you guys should remember that or have it on your cheat sheet. So 24 over pi times the radius, which is 0.01 squared, and that will give you a difference in pressure of 76,300 394 pascals. So that's your delta P. Okay. So now we can plug that into our equation. Viscosity is equal to delta P, which is 76,394 times pi times the radius, which is 0.01 to the power of 4. And that's over 8 times the flow rate, which is 3 times 10 to the negative 2 times the length, which is 1 meter. So you wouldn't have to put that 1 in there if you, because it's just 1. So that will give you 0.009999, which is rounds to 0.01. Okay, so that one just had an extra step in there to figure out the change in pressure. So just remember that pressure is equal to force over area. And if you have the radius, you can figure out the area. Okay. Number 11, we have a block of copper at 20 degrees Celsius, has dimensions of 10 millimeters by 40 millimeters by 20 millimeters. The block is heated to 200 degrees Celsius. How much longer do the 10 millimeter long edges of the block become in meters? And we've got the coefficient of linear expansion for copper, which is 17 times 10 to the negative 6. So what we're interested in here is just the change in one dimension, so one of the lengths. So here we just want the change in length is equal to LO, the original length, times alpha, which is the linear coefficient, multiplied by the change in temperature. So our original length was 10 millimeters, so that's 10 times 10 to the negative 3, or 0.01. So 0.01 meters times the linear coefficient, which is 17 times 10 to the negative 6, times our change in temperature, so it goes from 20 to 200, so that's a change of 180. And remember that when it's delta T, you don't have to convert it into Kelvin because it's the same. So delta T, you can just use the Celsius value. And that will give you 3.06 times 10 to the negative 5 meters, which is, so you can round that to 3.1 times 10 to the negative 5 meters. Okay. So next, number 12. Number 12, you wish to cool a 5 kg pack of steak from 25 degrees Celsius to 4 degrees Celsius. How much thermal energy must you extract from the steak to achieve this? And they want that in kilojoules. And you've got the specific heat, or the heat capacity of steak, which is 2.6 kilojoules. So remember that in physics, you need to have your energy in joules, not kilojoules. So you're going to have to convert 2.6 kilojoules into joules, which is 2,600 joules. Okay. So you've got a temperature change and you've got the specific heat. So that's going to be this equation here. Q is equal to mass times the specific heat times the change in temperature. So pretty straightforward. So mass is 5 kgs. The heat capacity is 2,600, or 2.6 times 10 to the power of 3. times the change in temperature, which is negative 21. It doesn't matter. We just want to find out the magnitude of the energy, so we don't have to worry about the signs. But if you were trying to be like completely accurate, it would be negative. So that's 21. And that will give you an answer of 273,000 joules. And you want that in kilojoules, so you'll just divide it by 1,000, which will be 273 kilojoules. Okay. Number 13, we have a cylinder containing 0.5 meters cubed of a diatomic gas at a pressure of 200 kilopascals and a temperature of 20 degrees Celsius. How many molecules of gas are there in the cylinder? So I actually think I've done this one in a previous tutorial. So sorry about that, but we can just go through it again. So I just learned the other day that there's no more diatomic, so they've taken that out of the course. But this is the same principle as if it was for a monatomic gas. So if it was diatomic, if it's diatomic, you use 5/2, right? But if it's monatomic, you use 3/2. So we're just going to carry on like the question says, so we can figure it out. But you'd use the same principles for a monatomic gas, right? Because they're still going to test you on monatomic gases this year. Okay, so we want to find out the molecules of gas, the number of molecules. So that's big N. So big N is the number of molecules. So don't get that confused with little n. So big N is number of molecules or atoms, whereas little n is the number of moles. Okay, so don't get confused by the two, and you should know which one's which. So you'll have two equations here. So you have PV is equal to little n times R times T, and you also have PV is equal to big N times K times T. Okay, so here we want the number of molecules, so that's going to be big N. So we're going to use this equation here, right? So we're going to rearrange it for big N. So big N is equal to PV, pressure times volume, over K times T. And so remember that, so I'll just go back for a moment. R is your constant, 8.3. So for physics, you just need to use 8.3. You don't need to use 8.314 like chemistry. I don't know why they do that, because like some values they use more significant figures and then some they use less. So it's, but anyway, for R in physics, you can just use 8.3, not 8.314. And then K is 1.38 times 10 to the negative 3, times 10 to the negative 23. So if you look on the model cheat sheet that I made, and it's on the Google Drive, I've just written down the values of R and K on that cheat sheet so that you don't get confused later on. Because on your formula sheet, they give you the values, but they have two K values. So they have a K value for electricity and a K value for this one here, which is different. So I'd just recommend writing down this K value next to these equations here so you don't get confused. Okay, so the pressure here is 200 kilopascals. remember that you have to convert that into pascals, so that's 200 times 10 to the power of 3 times the volume, which is 0.5. And that's over K, which is 1.38 times 10 to the negative 23 times the temperature. So temperature has to be in Kelvin. So that's 20 plus 273.15. So that's 293.15. And that will give you 2.5 or 2.47, but it's rounded to 2.5 times 10 to the power of 25. So, I mean, that's a huge number, right? So you've got, that's like, I don't even know how to say that. That's like 2.4 trillion, or something like that. And that's all within a box that's maybe this big. Okay, so that just gives you an idea of how many molecules there are, or how little these atoms are. Number 14, we have the temperature in a greenhouse next to the glass wall stays constant at 22 degrees Celsius. The outside air temperature is 18 degrees Celsius. So we have a difference of 4 degrees. So that's delta T. The surface heat transfer coefficient of the outside surface is 8 watts per meter squared per Kelvin. The greenhouse is made of glass that is 4 millimeters thick and has a thermal conductivity of 0.96. What's the rate at which heat is lost from 1 meter squared of the greenhouse wall? And we want that in watts. Okay, so we'll go through that again. We've got the temperature inside and outside, so the difference is the delta T is equal to 4 degrees Celsius. We've got the surface heat transfer coefficient, so that's the H. The H of surface is equal to 8. And then the greenhouse is made of glass that is 4 millimeters thick. So that's the thickness, which is D. D is equal to 4 millimeters, which is 0.004 or 4 times 10 to the negative 3. So I'll just write 0.004 meters. And then we have a thermal conductivity of 0.96. So thermal conductivity is K. So K is equal to 0.96. Okay. And then you want to find out the rate of heat loss from 1 meter squared, or from 1 square meter. So the surface area is going to be 1 square meter. Okay? And so if you have K and D, you need to find out the H of conduction. So the H of conduction, so this is through the greenhouse glass, is equal to K over D. So that's 0.96 divided by 0.004. And that will give you 240. So that's the heat transfer coefficient for conduction through the glass. Okay, so now we have the H of conduction. So we have the H of conduction and we have the H of surface. So you need to put them together to get your H total. So H total is equal to 1 over H of conduction. So I just write it like H to the power of -1. So that's the same thing as 1 over H plus the H of surface, 1 over the H of surface, so that's to the power of -1, and all of that to the power of -1. So that's going to be, so H of conduction is 240, 240 to the power of -1 plus 8 to the power of -1, and then all of that to the power of -1. So that will give you 7.74. So that's your H total. And then, so you want the rate of heat transfer. So rate of heat transfer is delta Q over T. And you're going to use H total multiplied by the surface area multiplied by the temperature difference. So that's H total is 7.74 times area, which is just 1, times the temperature difference, which is 4. So that will be 31. 31 watts. Okay, so it is a bit tricky. Quite a few steps. Yep.
Why is the -1 over?
Oh, so it's 1 over. So, yeah, 1 over. So that would be 1 over 240 plus 1 over 8. Yeah, but it's like adding resistance in electrical circuits. So if you have parallel circuits or parallel resistors, you're going to add them in parallel. And the reason you do that is because each of these H's represents a layer. So if you, and the bigger H is, the more heat you're conducting. Okay, so if you add a layer, remember when you get cold, you're going to add another layer, which is going to decrease the rate of heat transfer from your body to the outside, right? So if you add another layer, the total H should become smaller, not larger, right? So that's, and then if you add it like this, the total will become smaller, because you see how we added 240 and 8, but it became 7.74, which is smaller, right? So that's why we do that. Yeah. Okay. Number 15, an athlete has a work efficiency of 20%. In order to maintain a constant average internal energy and body temperature, she consumes 5 megajoules worth of food during an event. How much of this energy does she lose as heat during the event? And we want that in megajoules. So if she has a work efficiency, of 20%, what that means is that work is equal to 20% and heat is equal to 80%, okay? Because the energy that she uses up is only going to be turned into work or heat. Okay, so that's important to realize that. Once you realize that, it makes these questions a lot easier, because then you know that the amount of heat she's producing is going to be 80% of the total. So she's consumed 5 megajoules worth of food, right? So that's the energy that she's taken in, and that's just to maintain her average energy. So that's going to be equal. What that means is it's going to be equal to the amount of energy that she's used up. So, and 80% of that 80% of that 5 megajoules will be heat. So then the heat is equal to 0.8. So 80% of the total, which was 5 megajoules. So that will be 4 megajoules of heat that's produced, or 80% of the total. Okay, so that's the end of the basic tutorial, and we'll start again in 15 minutes. All right, cheers.